Time travel is real. It's happening right now, all around us, just not in the way science fiction usually imagines. We are all traveling into the future, 1 second at a time, but the laws of physics whisper that this journey doesn't have to be the same for everyone. It hints that the river of time can be bent, stretched, and maybe, just maybe, even looped back on itself. Tonight, we explore how clocks can slip out of sync, why the universe's ultimate speed limit and the pull of gravity are the keys to traveling forward, and what it would take to aim backward into the past. This is time travel, as understood in our universe. First, what do we really mean by time travel? Let's set aside the spinning dials and flashing lights. In physics, the definition is simple and profound. If two clocks start at the same time and place, take different journeys, and then disagree when they meet again, time travel has occurred. One clock has experienced more, or less, time than the other. This is possible because time is not an absolute universal metronome ticking away identically for everyone. It is a dimension, woven together with the three dimensions of space into a single, dynamic fabric. Space-time. A century ago, Albert Einstein completely revolutionized our understanding of this fabric. His theories of relativity showed that space-time is not a rigid stage, but a flexible entity that can be warped and distorted by motion and gravity. And when space-time is reshaped, the flow of time itself is altered. Move fast, and your personal clock slows down. Sit deep within a gravitational field, and your seconds tick by more slowly than for someone far away. This isn't a guess, it's a fundamental feature of our cosmos. Forward time travel is built into the very architecture of reality. Let's start with Einstein's special relativity, which deals with the effects of high speed. It reveals a phenomenon called time dilation. The faster you move through space, the slower you move through time relative to a stationary observer. Your onboard clock and your own biological processes will literally run slower than a clock you left behind. This isn't a mechanical error or an illusion, it's a genuine stretching of time itself, and it has been measured and confirmed again and again, with astonishing precision. The most famous illustration of this is the twin paradox. Imagine one twin stays on Earth while the other rockets out to a distant star and back at nearly the speed of light. When the traveling twin returns, they will be younger than their sibling. It sounds like a paradox, but it isn't. The key is acceleration. The traveling twin had to speed up, turn around, and slow down, breaking the symmetry of their journeys. In the geometry of space-time, their path was shorter. They genuinely experienced less time. We don't need to send twins into space to see this. Particle accelerators like the Large Hadron Collider prove it every single day. They accelerate subatomic particles called muons to 99.9% the speed of light. At rest, muons have a very short lifespan, decaying in just over 2 microseconds. But at these incredible speeds, their internal clocks stretch dramatically. They survive much longer from our perspective, long enough to be studied. The amount their time stretches is governed by a precise mathematical term called the Lorentz factor, or gamma. Even our astronauts experience this. Those living aboard the International Space Station are orbiting Earth at about 17,500 miles per hour. This speed slows their time down. However, there's a competing effect. They are in a slightly weaker gravitational field than we are on the surface, which actually speeds their time up. When you do the math, the speed effect wins. After a 6-month mission, an astronaut returns to Earth having aged a few microseconds less than the rest of us. A tiny, but very real, trip to the future. That brings us to Einstein's general relativity, which describes how gravity also bends time. General relativity tells us that mass and energy warp the fabric of spacetime, and we perceive this curvature as gravity. The stronger the gravity, the deeper the well in spacetime, and the slower time flows. Clocks run slower for observers deeper inside a gravitational well, and faster for those higher up, farther from the source of the mass. This effect is everywhere, though usually imperceptibly small in our daily lives. A clock on top of a mountain, where Earth's gravity is slightly weaker, genuinely runs a tiny fraction faster than an identical clock at sea level. Even taking a commercial airplane flight, where you spend hours at high altitude and high speed, leaves a measurable trace. The combination of speed and reduced gravity means your clock will be ahead by a few nanoseconds compared to one on the ground. This isn't just a curious footnote of physics, it's essential for modern technology. The Global Positioning System, or GPS, that your phone uses to find your location, would fail catastrophically without accounting for relativity. The clocks on GPS satellites tick differently from clocks on Earth by about 38 microseconds every single day, due to the combined effects of their speed and higher altitude. If engineers didn't constantly correct for this relativistic time difference, GPS navigation errors would accumulate at a rate of about 10 kilometers per day. Our ability to measure this is becoming almost surreal. Modern atomic clocks are so precise they can detect the time difference caused by a change in elevation of just a few centimeters. In laboratory experiments, physicists can lift one optical lattice clock just a foot above another and watch its tick speed up, exactly as general relativity predicts. These incredible instruments, using lasers and ultra-cold atoms in vacuum chambers, reveal gravity's subtle grip on the flow of time right here on a tabletop. So, how would you mount a serious journey into the future? You have two options, both derived from relativity. You could go incredibly fast, or you could linger near an incredibly strong source of gravity. In either case, your personal experience of time would slow down dramatically compared to the outside world. You would effectively skip ahead, arriving in a future you didn't have to live through second by second. The magnitudes required are immense. A futuristic starship accelerating to 99% the speed of light could make a journey that feels like 1 year to its crew, only to return to an Earth where 7 years have passed. To leap centuries or millennia, you'd need to get even closer to light speed. Alternatively, you could orbit a supermassive black hole. Near its event horizon where gravity is crushing, time slows to a crawl. Minutes for you could be hours, days, or even years for someone watching from a safe distance. Assuming, of course, you could survive the immense tidal forces that would try to rip you apart. Traveling backward into the past is a far harder and perhaps impossible proposition. While special relativity seems to forbid it by positing light speed as the ultimate limit, general relativity is more permissive. Einstein's equations allow for bizarre space-time geometries known as closed time-like curves, pathways that loop back and could, in theory, allow an object to travel into its own past light cone. Several theoretical candidates for creating such a curve exist. One involves the infinitely long rotating cylinders of mass proposed by Frank Tipler. Another, more famous idea is a traversable wormhole, a hypothetical shortcut connecting two distant points in spacetime. But there's a colossal catch. To keep a wormhole stable and open long enough for something to pass through, you would need a form of matter with negative energy density, exotic stuff that repels gravity. We've seen hints of it in quantum effects, but we have never observed or manufactured it at any meaningful scale. Another speculative possibility involves cosmic strings. These are hypothetical, one-dimensional defects in space-time, thinner than an atom, but with immense density, possibly formed in the early universe. If two such strings were to fly past each other at high speed, they could theoretically warp space-time in just the right way to create closed time-like curves. But first, we'd have to prove cosmic strings even exist. So far, the evidence is thin to non-existent. Even if we could build such a machine, many physicists believe nature has a built-in safety mechanism. Stephen Hawking's chronology protection conjecture suggests that the laws of physics themselves conspire to prevent travel to the past. One proposed mechanism is quantum back reaction. The moment a time machine opens a path to the past, virtual particles from the quantum vacuum could pour through the loop, creating a feedback of energy so intense that it would instantly destroy the gateway. Nature, it seems, may violently censor any attempt to edit history. And then there are the paradoxes. The most famous is the grandfather paradox. What if you travel to the past and prevent your own grandparents from meeting? You would never have been born to build the time machine in the first place, creating a logical contradiction. How can physics resolve this? A few intriguing, though unproven possibilities have been proposed. One answer is the Novikov self-consistency principle. It states that any event that occurs on a closed time-like curve must be self-consistent. In other words, the probability of any event that would create a paradox is zero. You can travel to the past, but you cannot change it. You can try to stop your grandparents from meeting, but some improbable event will always conspire to ensure that you fail. Your presence in the past was already part of the history that led to your future. Another, more radical idea, comes from the many worlds interpretation of quantum mechanics. In this view, any action you take that could change the past doesn't create a paradox. It simply causes the timeline to branch into a new parallel universe. You could prevent your grandparents from meeting, but you would do so in an alternate timeline, not your own. Your original timeline remains unchanged, and you are now a visitor in a new one. It's a fascinating concept, but remains highly speculative. So, if time travel to the past were possible, what evidence should we be looking for? We haven't found any time travelers, but we can search for the exotic physics that might enable them. We use arrays of radio telescopes to precisely monitor pulsars, the universe's most stable clocks, looking for any strange deviations that might signal a disturbance in space-time. We analyze data from gravitational wave observatories, searching for ripples from bizarre objects that don't fit our current models. So far, space-time appears to be behaving exactly as predicted by relativity, with no verified shortcuts to yesterday. The search continues, with every upgrade to our instruments, more precise optical clocks, next-generation GPS satellites, more sensitive gravitational wave detectors like LIGO, Virgo, and CAGRA. We push the limits of what we can measure. Future space missions designed to fly near the sun or other massive objects will provide even more stringent tests of general relativity in strong gravity regimes. Each new experiment is a chance to see if there's a crack in our understanding, a loophole that might one day be exploited. In the end, the story of time travel is a tale of two directions. Travel to the future is not only possible, it's an unavoidable, measurable, and technologically useful fact of our universe. Travel to the past, however, remains firmly in the realm of theoretical physics, plagued by paradoxes and seemingly forbidden by immense practical and fundamental barriers. It is unproven, and perhaps unprovable. But the questions it raises are what drive science forward. Until we know for sure, we will continue to test, to doubt, and to refine our picture of reality. Stay curious.